With word problems, I like to look at the last sentence. We're supposed to find the instantaneous rate of change of the temperature at 6 p.m. So it depends on what they decide, what they say T is. So Homer sets the thermostat. The temperature of the house begins to drop from 45 degrees Fahrenheit, reaches a low of 30, and then rises back to 45 by 11 p.m. They give us a function where T is the number of hours past 1 p.m. Okay, that makes sense. So we're supposed to find the rate of change in the temperature at 6 p.m. That means T equals 5, because T represents the number of hours past 1 p.m. So that'd be 5 hours past. So to find the instantaneous rate of change, we're looking for T prime of T prime of 5, I should say. The instantaneous rate of change. That's what this notation means. The derivative, or the instantaneous rate of change at 5. And so in order to do that, we could use either of those definitions of a derivative. I guess I like this one best, when it's f of x minus f of a over x minus a. That one tends to come in handy more often. Oh, sorry, this is the limit as x approaches a. So that's what we want to evaluate here. The limit as x approaches 5 for f of x. In this case, it's t instead of x, right? We got 0.6t squared minus 6t plus 45 minus f of a. So if we were to plug 5 in here, what's the value? We can do that by doing 5 squared times 0.6. And we minus that by 30, because that's what 5 times 6 is, plus 45. So it looks like we got a temperature of 30 degrees at 6 p.m. And then we're supposed to divide that by x minus a. So x minus 5. Oh, I wrote x. T, right? We're talking about t minus 5. And I wrote x over here. This is all the variable t. Okay, let's see. What else we got to do? So it'd be nice if we could factor it. Let's see if we can. Because right now we have indeterminate form. We can't just plug in 5 for t. If we combine these, that's 0.6t squared minus 6t plus 15 over t minus 5. I bet we can factor the back part. So if we use that longer method factoring, 0.6 times 15, that comes out to be 9. We're looking for two numbers that multiply to be 9, but add up to be -6. So how about negative? Oh no, I don't think we can without decimals. That's no good. Here, instead, let's try doing this. I think it still won't be factorable. I'm just going to factor. I'm going to divide everything in the top by 0.6 to try to make it easier to look at. 0.6. That way the leading coefficient is 1, and that makes it easier to factor problem. Right, but -6 divided by 0.6. That's -10. And then 15. If you divide by 0.6, it gives us 25. Okay, this is something easier to factor. So if you've ever heard that algebra is the hardest part of calculus, you're seeing why, because that trick isn't something that students usually look for, but you can factor 0.6 out of everything, and then we can factor the numerator. Two numbers that multiply to be positive 25, but have to be -10. And so the t minus 5's cancel. And so now we can directly plug in 5 for t. 5 minus 5 makes 0. 0 times 0.6. This whole limit is 0. So the instantaneous rate of change at 6 p.m., in other words, when t equals 5, we just found out is 0. So we have data this time. We're asked to estimate the instantaneous slope by taking the average of two rates of change. We can't get the instantaneous slope, but what we could do is we could estimate it. Like the rate of change between these two values is 344. It went up by 344. And then the rate of change between these two values is 64 So that's 1 to the left of 2009, 1 to the right of 2009. If we add those together and divide by 2, then we got an estimate for the average rate of change. And our estimate's 204 using the data points that are directly to the left and to the right of 2009.